Okay, good evening guys. Welcome back to yet another video on Foundations of Math 2. I'm Mike. In some of our previous videos, we talked already about how to construct tree diagrams. In this video, we're going to use those tree diagrams to help determine probabilities of events happening. So, as you can see, we already know how to make tree diagrams to identify all possible outcomes that are in a sample space. You have a probability experiment. You have a particular event that you're focused on. We can use a tree diagram to visualize all possible outcomes. The probability experiment. That is, we can come up with our entire sample space. And then let's carry it one little step further and calculate some probabilities with them. So first example, you roll two identical four-sided dice, and on each side of each die there's the numbers 1 through 4. Create a tree diagram to represent all possible outcomes, and then we're going to use that to find the probability that the sum of the numbers rolled is greater than 6. So first, let's see what our tree diagram is going to look like here. We're taking two four-sided dice. We're rolling them both. So the first die you roll, you can have one of the following outcomes: 1, 2, 3, or 4. And now from there, you have now your second roll. You can roll a 1, a 2, a 3, or a 4. 1, 2, 3, 4. One, two, three, 4. 1, 2, 3, or 4. So this is a very rough yet still accurate tree diagram for the sort of possible outcomes you could have. If you wanted to, you could sort of connect these guys here. And then that looks more like a tree, but really it's just first roll, and then you have your follow-up roll after that. So this is our tree diagram. We want to know the probability that the sum of the two numbers that we roll is greater than 6. Now, just doing some quick mental math here, if you roll two dice, and on each die the largest number is 4, then the largest possible sum you can have is 8. 4 plus 4. We want the probability that the sum is greater than 6, which means we want the probability that the sum is 7 or that the sum is 8. So let's find all the outcomes here that have the result of the sum of the two numbers being 7 or 8. 1 plus 1 is 2, not what we want. 1 plus 2, no. 1 plus 3, no. 1 plus 4, no. 2 plus 1, no. 2 plus 2, no. 2 plus 3, no. 2 plus 4 is 6, but we want something greater than 6, so that's not there as well. 3 plus 1, no. 3 plus 2, no. 3 plus 3, no. 3 plus 4, yes, because the sum of those two numbers is 7. Last time I checked, 7 is indeed greater than 6, so this is one of our outcomes that we want. 4 plus 1, not good. 4 plus 2, not good. 4 plus 3 is good. That sum is 7. And then 4 plus 4 is good. That sum is 8. So, the probability of this event E and I'll say that the event E is the sum of the numbers rolled being greater than 6. Give that the name E. This is the theoretical probability that we are calculating here. And for theoretical probability, it's the total number of outcomes that are in the event E divided by the total number of possible outcomes in the sample space. So we had 1, 2, 3 events that are in the event. How many how many possible outcomes are there in the entire sample space? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13, 14, 15, and 16. So there we go. That's our probability. We have a 3/16 probability that when we roll these two four-sided dice, the probability that the sum of the two numbers will be greater than 6 is 3/16. So we're just doing something that we already know how to do, which is create a tree diagram for a particular scenario, and we're going to use that to figure out how many outcomes are in the event, and it's that number divided by the total number of possible outcomes in that sample space. Suppose we flip a fair coin 3 times. Using a tree diagram, find the probability that you get 2 heads and thus 1 tail. We're going to rule out the very, 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 very small possibility that the coin lands on its side. That almost never happens. So again, let's create a tree diagram. Take a fair coin, flip it 3 times. So I have my first flip, heads and a tails. Okay. From there, my second flip, I can have another heads or I can have a tails. For my first flip being a tails, I can have a heads or a tails. So these are all the possibilities through 2 coin flips, but we're doing 3 coin flips. So from each of these, we could have heads or tails coming up. So HT, 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 HT. So we are looking at trying to find the probability that you get 2 heads and 1 tail. It doesn't matter the order in which you get the 2 heads. It doesn't say that you have to get your 2 heads in the first 2 tosses. We just want 2 heads and 1 tail. So let's figure out how many of these outcomes have 2 heads and 1 tail. That's 3 heads. That's no good. That's 2 heads and 1 tail. This is 2 heads and 1 tail. That's a heads and 2 tails, not good. 2 heads and a tail, there. 2 tails and a head, not good. 2 tails and a head, not good. And 3 tails, no good. So again, we had 3 outcomes where we have 2 heads and 1 tail, the thing we want. So again, theoretical probability, number of outcomes in the event divided by the number of outcomes in the entire sample space. 3 was the number of outcomes in the event. How many total outcomes do we have in the sample space? 1, 2, 3, 4, 5, 6, 7, 8. So 8 possible events, 8 possible outcomes in the entire sample space. The other way you could have figured out how many outcomes you had in the sample space, was just add up how many letters, or add up how many things you had going down this column. 1, 2, 3, 4, 5, 6, 7, 8. But pretty straightforward to use tree diagrams to come up with probabilities of events happening. Nothing super complicated happening here. We're just really combining the basic formula for theoretical probability as well as tree diagrams, which we know how to work with. It's getting late. Well, we can use things besides just tree diagrams to figure out probabilities. We can also create tables, and we can create tables to identify all possible outcomes and use those things to find probabilities as well. So suppose you roll a 4-sided die and a 5-sided die. Let's create a table of outcomes for the rolls of these two die, and then we're going to use that to find the probability that both rolls are odd. So let's sort of make a, as you said, table or chart here, if you will. And I'm going to put the roll of the first die over here. The first die is the 4-sided die, so I'm going to write those possibilities. 1, 2, 3, 4. And then we have the second die, the 5-sided die. So 1, 2, 3, 4, 5. So now I'm just going to represent each of the possible outcomes that we have as a result of rolling these two dice. I'm going to write them as ordered pairs. So I could have rolled a 1 and a 1, could have rolled a 1 and a 2, a 1 and a 3, 1 and a 4, and then a 1 and a 5. 2 and a 1, 2 and a 2, 2 and a 3, 2 and a 4, 2 and a 5. And I think you see how this is going to be finished up here. The first number written is always the result you get for the first die being rolled. The second number you write is always the result of the second die being rolled. 3, 1, 4, 1, 3, 2, 4, 2, 3, 3, 4, 3, 3, 4, 4, 4, 3, 5, 4, 5. So there's our full table. These are all the possible outcomes we can have for rolling a 4-sided and a 5-sided die and simply noting what the results are. So now we just need the probability that both rolls are odd. So again, if the event is both rolls being odd, P of E is going to be the number of outcomes that are in the event divided by the number of outcomes there are in the entire sample space. Well, perhaps the easier one, how many possible outcomes are there in the entire sample space? Well, we just count up the number of ordered pairs that we have here. 1, 2, 3, 4, 5, 10, 15, 20. So 20 is going on the bottom. The number of outcomes that are in our event E. E is both rolls being odd. So let's just underline all the outcomes that have both numbers in it being odd. 1, 1, 1, 3, 1, 5. Even, every number or every ordered pair in this row has a number that's even, so that's not good. 3, 1, 3, 3, and 3, 5, and then every entry in this row has a number in it that's even as well. So there's only 1, 2, 3, 4, 5, 6 possible outcomes that are in the event E. There are 6 outcomes where both numbers are odd. So the probability that both rolls are odd is going to be 6 over 20. And typically we write this in simplest form. We cancel out common factors if we can, and we get 3/10 or 0.3. So that is our sample here. The second one, I'm going to challenge you guys. Try this one on your own. Suppose you have 15 cards, and these cards are the numbers 2 through 6 in the suits of hearts, clubs, and diamonds. What is the probability that the card you pick at random is red and less than 4? So come up with a table consisting of all the possible outcomes you can have, and then try to figure out what the probability that if you pick a card at random, it's red and less than 4. So pause the video here. Once you think you have it, press play, and we will see if your answer is correct. All right, guys, let's see what you came up with. Here is my table. I broke it out down the left column here. I had the suit, H for hearts, C for clubs, D for diamonds. I teach math, not art, so I can't draw. Yeah, the hearts and diamonds might not have looked bad, but the club would have just looked awful. So I did H, C, and D. And then across the top, I did my numbers 2 through 6. So these are the 15 cards I have. The 2 of hearts, 3 of hearts, 4 of hearts, 5 hearts, 6 of hearts, and then similar with clubs and diamonds. So my event is that the card I pick, the one card I pick, is red and less than 4. So I need to find what P of E is. But on the bottom, again, this is theoretical probability. The number on the bottom is going to be the total number of outcomes that are in the entire sample space. So how many possible outcomes can we have total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 is going to be the number on the bottom. Now, how many outcomes are there that are in my event, capital E here? How many cards here are red and less than 4? Well, in a traditional 52 card deck, your red suits are the hearts and the diamonds. So I have hearts, I have diamonds. I need the numbers that are less than 4. 2 of hearts is red and less than 4. So is 3 of hearts. Can't take 4 of hearts because 4 is not less than 4. We don't need any of the clubs because the clubs aren't red. And then 2 of diamonds is red and less than 4, same as 3 of diamonds. So I have 1, 2, 3, 4 separate cards that are in my event capital E. And the probability of this event happening is 4 out of 15, or 4 over 15. So hopefully that's what you came up with as your final answer. So guys, this concludes our video on using tree diagrams and tables to calculate some theoretical probabilities. There's really not much that's brand new to us here in this video. For the most part, this is all already stuff coming from previous videos in this chapter. We already knew how to calculate theoretical probability coming into this, and we already knew how to set up tree diagrams. The only thing that's kind of new is coming up with the tables. And a table is really just another way to represent a tree diagram. There's in the grand scope of things, there's really not much of a difference between a tree diagram and a table. So guys, if you have any questions or comments, please be sure to reach out to me. Emails, texts, phone calls, flare guns up in the sky, banners soaring through the air, taking the stars in the cosmos and rearranging them to say, help me, whatever you have to do. Otherwise, until the next video, take it easy, guys.